Here's another example of partial fractions. Normally you look at this and you'd say, well, x should be the secant of theta, etc., etc., etc. But you could also look at this as 1 over x plus 1 times x minus 1 dx, which splits into partial fractions as a over x plus 1 plus b over x minus 1 dx, which if you recombine it becomes what? A times x minus 1 plus b times x plus 1 all over x plus 1 x minus 1 dx, and all we have to ensure is that these numerators are the same. One trick is to say when is 1 equal to a times x minus 1 plus b times x plus 1? One thing is to try x equals 0. X equals 1. If x equals 1, we get 1 equals 0 plus 2b. So b would be 1/2. And if you try x equals negative 1, you end up getting 1 equals negative 2a plus 0. So a is negative 1/2. Or you could multiply it out and you'd say ax minus a plus bx plus b equals 1. And so you say the coefficients of the x's, the a plus the b has to be 0, and the constants, the minus a plus the b has to be 1, and you can do this with simultaneous equations. But in any case, a is negative 1/2, b is 1/2, and there's so much in between. I will copy this down like so. And so this is what? Negative 1/2 over x plus 1 plus 1/2 over x minus 1 dx. I'm really tempted to just pull the 1/2 out front. 1/2 minus 1 over x plus 1 plus 1 over x minus 1 dx. And this isn't so bad. This is 1/2, and again, minus the natural log absolute value of x plus 1 plus the natural log absolute value of x minus 1 plus c. Yay! So it is a big advantage. Is this better? If we had done integration by parts, what would we have gotten? 1 over square root of... Wait, what was this? This was the integral of 1 over x squared minus 1 dx. If x were secant of theta, dx is secant theta tangent theta d theta. So we would end up with, let's see, 1 over secant squared minus 1 is tangent squared. So this is 1 over tangent squared of theta times secant of theta tangent of theta. And one tangent goes away. And oof, what do we do with that? There's the d theta here. Do we turn this into sines and cosines? Do we say 1 over tangent is cotangent, which is cosine of theta over sine of theta, and secant is 1 over cosine of theta d theta. So these cosines cancel out. I'm beginning to think that this is not better. 1 over sine is cosecant. Cosecant of theta d theta, and you probably have no idea, but if you take the cosecant of theta and you multiply it by cosecant of theta plus cotangent of theta over cosecant of theta plus cotangent of theta d theta, does this work the same way? If u is the cosecant of theta plus the cotangent of theta du, the cos are just the same but negative, right? The derivative of cosecant is negative cosecant theta cotangent theta, and the derivative of cotangent is negative cosecant squared of theta, the whole thing d theta, and that is the negative of the top. So negative du is the top. So we would say that this whole thing turns into the integral of negative du over u, which is negative the natural log absolute value of u, which is cosecant of theta plus cotangent of theta plus c. Now, if you had that memorized, then this might not be so bad of an integral. And what do we have? X is secant. X is the secant of theta, so there's some angle theta here, and secant is hypotenuse over adjacent, so this must be x squared minus 1. Hey! That's the thing, where is it? That's the thing that we had originally, although it's a square root, but so what? So we've got the equals negative the natural log of cosecant is 1 over sine. Sine is this over this, so it's x over square root of x squared minus 1 plus cotangent, which is 1 over tangent 1 over square root of x squared minus 1. There's a common plus c. We have a common denominator in here, negative natural log of x plus 1 over square root of x squared minus 1 plus c. Oof. Anyway, this is the same answer. You can break this up into the natural log of x plus 1. Where is it? The natural log of, x minus 1. Oh, wait. Natural log of x plus 1 is right there. And the 1/2 explains the square roots. I'm going to stop here. Suffice to say, partial fractions can be a whole lot better. Let's be done with this.